Hello and welcome to Empowered Learning. This video will be about solving optimization problems. What optimization problems are essentially word problems where we are trying to minimize or maximize something. And in the world of calculus, we use derivatives to help us to be able to minimize and maximize. So another way of putting what it is that we are about to do is we are going to be doing word problems where we're going to be using either the first and or second derivative to help us to be able to maximize or minimize something. Now, for these types of problems, the two main tools that we use is either the first derivative test or the second derivative test. Because in maximization or minimization problems, the main thing that we are trying to find is information about either a local max value, or when a local max happens, or a local minimum value, or when that local min happens. And so the first derivative test and the second derivative test both help us to be able to find local max and local min values and where those local max and min values actually happen. Okay. The first derivative test, and we're going to go over it for this version of it for global max and min values. And it's worded that way because in these problems, we're modeling something to where we're either going to have either one local max or one local min location, and that is it. Okay. We know that in studying the first and second derivative tests earlier, in some of the earlier videos that I posted here, we know that we could have multiple locations of a local max or local min. We could have multiple locations for a global max and or global min. Okay, but specifically for these types of problems, we're going to have either a local max or a local min. And that local max or local min is going to also double as a global max or global min respectively. Okay. So we'll first go over what the first and second derivative tests say again, and then we'll just jump right into several examples of how we actually use this, or use these tests, I should say. So for the first derivative test, we want to suppose that C is going to be some critical number. And if you remember, a critical number is just a number that tells us that, hey, we have the potential of having a local max or a local min there. Specifically for these types of problems that we're going to deal with, we're going to look specifically at the form of the critical value to where we get the smooth peak or the smooth dip in our graph, okay? And of course, that lets us know where we have horizontal tangent lines. Remember, for a critical value, the other type situation that we have here is the value of C that we plug into the derivative, and we'll get the does not exist case. And so normally, if we're modeling something to where we either have a corner or a cusp in the problem, we'll end up with a situation like that, but none of our problems that we will look at here will be that way. So we won't be worried about this version of the critical value. So again, we are trying to find a value C that will satisfy this equation here, which is going to tell us that we have either the potential of having a local max or a local min. Okay. And if we find that, then the first derivative test just basically says we need to test for values around x equals C. Okay. And so I'll go ahead and bring down this visual down here just to make my point. So here, if this is x equals C here, we pick a test value that is smaller than C, pick one that is larger than C. And we plug these test values, I'll call them C1 and C2, into our first derivative. If our first derivative ends up being positive for any of those values, where x is less than C, where C1 basically, and then we choose C2, plug it into our our first derivative, and it ends up being negative, then we see we have a case where our graph goes from increasing to decreasing, which basically means we have a local max at x equals c. Okay. Now, part B is just the opposite. So instead of us, let me go here again. So we have the same C1, C2. If we plug in C1 and we get values for the first derivative that are negative, and then plug in C2 and get values that are positive, then we have a graph that went from decreasing to increasing. So therefore, this lets me know that I had a local min at x equals c. And so we exploit this fact about the first derivative test to help us to be able to determine if a critical value is indeed the location of a local max or a local min. And in these problems, it is required, necessary, mandatory, I don't know how else to put it, that you do this step of actually verifying that your critical value is indeed a local max or local min before moving forward in problems of this type. Now, the second derivative test does the same thing as the first derivative test in that we want to find out where our local max and local min, whether we have a local max or local min at a critical value. Okay. Now, remember again that this local max or local min is also going to be a global max and global min, because that's going to be the only one that's in the model of the problem that we're working on. Okay. But notice that the second derivative test uses critical value and the second derivative to be able to determine whether we have a local max or local min. And so what the second derivative test is doing is using what we know about concavity of a function to help us to be able to determine if we have a local max or local min. So in short, if we find this critical value c that we're talking about, and we plug it into the second derivative of our function, and we see we get a negative value, then what that tells us is that, first of all, the original function was concave down at x equals c. And as you can see from the graph here, if we have a critical value, which is a place where we either have a local max or local min there, and we see that it's concave down, that's telling us that which one of those choices I need to choose is the one to where I have a local max. Okay. And so since I have a local max there, and since it's the only one, it will also be a global max. So this lets me know that I have a local / global max at x equals c. If I take my critical value again, plug it into the second derivative, and I get a negative value for an answer. So similarly, if I take my same critical value, plug it into the second derivative, and I get a positive value, then that lets me know that the original function was concave up, and thus I have a local min at x equals c. And since that's the only one, that local min will also be a global minimum value. Okay. And so for these problems, other than being able to model our situations, this is pretty much all we need to know. So let's go ahead and jump into some of the examples so that we can see how to approach some of these problems and how the first and or second derivative will fit into it. Okay. Now, before I do that, I do want to make this statement before we begin. For most people, the best way for you to get good at word problems is just to do more word problems. Expose yourself to more word problems. There is no one way to say, if I read this word problem and I understand this one thing, I'll be able to get any word problem at any time without having to think much about it. It just doesn't work that way. Okay. Unless you're really, really special, and unfortunately, I'm not one of those people, you will have to work at it and expose yourself to many, many different types of problems to get really good at some of these word problems here. Okay. So I don't want you to get frustrated if at first glance you're like, hey, I don't really understand what's going on. It does take practice. Okay. And so the more you see them, the more you practice them, the better off you will get and the faster you'll get at solving. Okay. All right. So let's jump into some examples now. Okay. So our first example here is a classic example, and the context of the problem could be various things. Of course, in the context of this problem, we have an architect that wishes to enclose a rectangular area and then divide that area into 3 equal spaces with sides parallel to one side of the rectangle. Basically, they're trying to take some area and partition it into 3 different parts. Okay. And what we want to know here is based upon how much total, bordering or fencing that we have available. We want to figure out what's the largest area that we can enclose. Okay. We could change the context of the problem, but essentially we're taking a rectangular area, dividing it up, and we want to see based upon how many actual sides of this particular shape we have, what's going to be the largest area available to us. Okay. So this is actually a pre-calculus or / college algebra type of problem. And so I say that because we can actually solve this problem by using algebraic techniques versus calculus techniques. But the purpose of this problem is to show you how to do this the calculus way. And so I say that because if you're taking a course and you're looking at a problem like this and you want to solve it, and you're in a calculus course, you will probably not get credit for solving it the algebraic way in a calculus course. Okay. So I want to go ahead and put that out there that when in calculus, do calculus things. When in algebra, do algebra things. Okay. All right. So for this problem here, we see that we have this rectangular area, and we're told to partition it into 3 different separate areas. And we're ignoring the thickness of whatever bordering that will be along here for these 2 inside border wall partitions. Okay, we're ignoring that, the width of those. So the width of that is negligible, so it's not taking away from the area any. So with that, we basically want to be able to model the area. And of course, we know that in general, the area of a rectangle is going to be length times width, where we will call x here the length and y the width. Okay. And of course, I have that stated here. Now, we also know that the perimeter of any given shape, okay, by definition, perimeter is just sum of all the sides. So if I add up all these sides, so I add up 1, 2, 3, 4, 5, 6. If I add up all those sides, I know that the total amount of material that I have to enclose this space is 1,000 feet. So if I scroll down here, I know that sum of all sides, a total of all sides, which formal name for this is perimeter, is going to be 1,000, and that's going to equal 2 times the length here, plus 4 times the width here. Okay. And so we have that along with the fact that area is equal to length times width, and we have all the information that we need to model this situation, so that if we find out what the area is going to be as a function of x, we can pick the x value that's going to give us the largest area to enclose. Okay. So here it says we need to find the dimensions for x and y in order to maximize this area. We're going to use the perimeter equation to help us be able to rewrite our area equation as a function of x. So here's our perimeter equation. And basically what I'm doing here is I'm solving for y. Okay. Now, why am I solving for y? Because I'm choosing to express y, meaning choosing to express what I have, this width here in terms of x. Okay. I could just as simply say I want to solve for x and express x in terms of y. Nothing wrong with that. Okay. It's just a little bit more conventional to rewrite a function in terms of x than it is for y, so that's why we're doing it. So here I just need to solve for y, so I subtract 2x from both sides, divide both sides by 4, and I see that y just ends up being 250 minus 1/2 x. And so if we remember here, area is going to be x times y, or length times width, and since y is all this business here, we can just plug it in. And that's exactly what you see here. So once we distribute the x to both terms, now we have a quadratic function. And of course, this quadratic function here is going to be opening down. So in general, this is what this function looks like. And so again, I'm approaching this from an algebraic perspective right now, just so that you can understand that, yes, we are indeed going to have a local maximum here, okay? Now, we're actually going to show that by finding the critical value and also verifying via either the first or second derivative test that we do have a local max at, whatever x value the critical value is. So, but from our algebra knowledge, we already know kind of what the outcome should be, or what it should at least look like, okay? So to find the critical value, we need to take the derivative of this function here. And since it is a polynomial, we're only going to consider the case when the derivative is equal to 0, because we know that for polynomials, taking the derivative of this and saying does not exist, we're not going to have a situation like that, okay? So we take the first derivative of this function. I'm going to change colors here. So we take first derivative of this function. Of course, we do that here. And afterwards, we see that we just get minus x plus 250 is equal to 0, which means x is 250, okay? And so this would be our critical value, or this, in terms of this problem here, remember, x is equal to length. So what this is telling me here, and I'm going to erase some of this to make this be a little bit more clear. So what this is saying here is that we know that a length of 250 feet for x. So for this length right here, if I choose it to be 250 feet, then the total area that I get within this rectangle is going to be the largest possible. Okay, so that's what that critical value means. Now, all a critical value tells us is that we either have a local max or a local min. Okay, mathematically, critical value does not say, yep, I got a local max or a local min. It just tells you the potential locations where you got it. We actually have to use one of these tests to be able to show that we actually have a local max or local min. And we choose the second derivative test because it's actually relatively easy to do here. So remember, we found that the first derivative of our function here was this negative 1/2 times 2x plus 250, which is essentially what we had here. So therefore, the second derivative is just going to be minus 1, okay? Because derivative of minus x with respect to x is just minus 1. Derivative of a constant is 0. And so we see here that for all values of x, doesn't matter what it is, the second derivative is going to be negative. Hence, this means that my original function was concave down, exactly like how we set up here before. And thus, we have a global max value, local max / global max, at when x is equal to 250. Okay. So now that we have that information, we can now use what we know about area here. Particularly, we know what x is now, and we know y is just 250 minus 1/2 x. We can use that information to find out what is going to be the largest area enclosed. And so here we see that our length at a maximum was just 250. Our width at a maximum is just that 250 minus 1/2 x. But of course, we plug in 250 for x, and we see it's 125. So if we just multiply 250 feet by 125 feet, we get 31,250 square feet. And that will be the largest area that we will be able to enclose with 1,000 feet of material, okay, to enclose the area with. All right, let's move on to the next example. So the example that I'm going to do here and the next one after that are going to be very similar in that we have a little geometry going on here, but not anything too tough. This problem says that we have a rectangle that is constructed with this base on the x-axis. So we have this rectangle here where its base is where I'm drawing here. Okay. And two of its vertices, meaning two of the corners of the rectangle, is basically intersecting a parabola. And that parabola is going to be 25 minus x squared. Okay. So that's parabola opening down. And we want to know what are the dimensions of this rectangle here, meaning the length and the width, to maximize the area under this particular parabola. Okay. So we basically want to know what is going to be the largest rectangle we can basically stuff under this parabola here. Okay. Now, notice that this function y equals 25 minus x squared, this function is symmetric to the y-axis. So we are going to use that as an advantage to us to help make modeling our problem a little bit easier to do. Okay. So the first thing that we see here is that instead of me looking at this total length here, looking at this total length here as x, I can just look at half of the rectangle as x, okay? And so my point here is that if, let me erase this right quick. So if I know that this length from here to here is x, then I also know that this length from here to here is x, okay? And this is exactly what I need to know to kind of characterize what this particular point would be. And so I notice here that the height of my rectangle here, I'm characterizing it as my width in this case, because I'm letting, in this case, the length be the x, or as you're going to see later, 2x, and we're going to let the width here be y, okay? So we see that for a given value of x, corresponding y value is going to be 25 minus x squared, which is just the height of the parabola, okay? Now, as far as the actual length of the rectangle, we see that we know this length is x and this other length here in the red is x. So the total length of the rectangle is just 2 times x. So here, this is why we have 2 times x as the actual length, and y, which can be represented as 25 minus x squared, as the actual width. Okay. So once we put that together, we see that we end up having this cubic function that will characterize the area. Okay. Now, one of the things that we have to remember here is that we are using a polynomial, which is defined for all real numbers, to be able to model a situation here where we won't be able to use all real numbers for x, okay? And to be very clear here, the domain, or the values of x that actually make sense for this particular problem here, are going to be all values of x in between -5 and 5, okay? Not including -5 and 5, because if I let x equals well, in this case, if I let x equals 5, because having a -5 really didn't make a whole lot of sense here. But I'm just talking about in terms of going from this point to this point. If we were to let x equal 5 or -5, then we know that our rectangle would have a an area of 0. Okay, because if x was -5 or 5, then y would be 0. And that's not possible for our situation, so we have to exclude -5 and 5 here. Now, in knowing that, we know that this particular function for this situation is only going to work for values strictly in between -5 and 5. And if we want to be, totally correct, we know that x has to be greater than equal to 0 in this case. Really greater than 0 to be, actually accurate. But no, we could have x equals 0 in this particular case if we wanted to. We would have to have it be that way because, of course, length is supposed to be non-negative. Okay. All right. So if we look here, we take the derivative of this particular function. We see that we would get something that looks quadratic. And if we go and solve that for x, then, of course, after doing some algebra and whatnot, we see that x is going to be 5 divided by square root of 3. And, of course, that is the exact value for it. Okay. And I'm leaving it in exact form because it'll actually make it easier for me to solve the problem that way. For those of you that have to know what that is, that's roughly about 2.88. Okay. So in this situation here, knowing that x is just 5 divided by square root of 3, or x is roughly 2.88, just lets us know that from a math perspective, we either have a local max or a local min at this particular value. And again, we're going to use the second derivative test to be able to confirm, or find out rather, that this particular critical value is referring to a local maximum. Okay. And so to find the second derivative, we take the derivative of the first derivative that we got, and that's just going to be a minus 12x when we do. We plug in a positive number and multiply that times a negative number, and we get a negative number as a result. And since the second derivative is negative, we know that the original function had to be concave down then, which again makes a whole lot of sense because here we're talking about area and whatnot. All the stuff is enclosed under a parabola, so the height of it is sort of modeling the height of the parabola as well. So it makes sense that we would have this concave down type function for the original area, or the original model for the area. So that means we have a global max there. And so what this means for us, since we needed to find out the dimensions, we could use this 5 divided by square root of 3 to figure out what the length and width would be of our rectangle at maximum area. So of course our length was 2 times whatever x was. So that's going to be the length at a maximum is just going to be 2 times 5 divided by square root of 3, which is 10 divided by square root of 3 units. And of course the width is going to be the height of the parabola. So we're just going to take 5 divided by square root of 3 and plug it in for x into that. And we see that we end up getting 50 over 3 units for that result. So our dimensions here in terms of length is just 10 divided by square root of 3 units. In terms of width, that is going to be 50 divided by 3 units. So again, for those of you that just have to have this in decimal numbers, this is roughly about 5.77 units. And I haven't found out the other one yet. So now, yeah, so the other one is like 16.67 units if you want to approximate. Okay. And here we haven't specified whether we're talking about feet, centimeters, or whatever. So we're just calling it units there. Okay. All right, let's move on to our next example. All right, so for our next example here, we see that we have a similar type problem, but instead of trying to stuff a rectangle under a parabola, we're trying to stuff it inside an isosceles triangle. Okay. And so you can see the figure here in how we actually are trying to stuff that rectangle under or inside of an isosceles triangle. And For this one, we're trying to get the largest rectangle that we can, okay? So this problem says, given this figure that we see right here, it shows a rectangle inscribed in an isosceles right triangle, and we know the hypotenuse is going to be 14 units long, and that's the hypotenuse of the bigger outside isosceles right triangle, okay? And so remember that isosceles triangles are just triangles where two of the sides are equal to each other. And of course, the hypotenuse is going to be the longest side. And what we've done here to make it convenient is we've drawn the hypotenuse with a coordinate system to where we've kind of divided the isosceles triangle in half, where we have 7 units here on the left side, another 7 units here on the right, okay? And so this just, we're doing it just to make modeling a little bit easier to do. So the first thing we're asked to do is express our y coordinate of P. So in other words, this point here, we want to find its y coordinate in terms of X, okay? And this says we want to write an equation of a line for this. I didn't do that, but we can do that. I kind of use geometry to do it. But we can do it both ways. To me, it's just easier to actually do it the geometry way, because when we do it, we just get our answer and we just move on. So, all right. So express the area of this rectangle here in terms of X. And then after that, once we're able to model that, then of course, we're just going to take the derivative of the area, set it equal to 0, find out the critical value, and use either the first or second derivative test to confirm that our critical value is going to be, in this case, a local maximum. Okay. All right. So the hard part of this problem is trying to figure out what is going to be the y coordinate here of P. So if we look, just like how it was in the other problem, the what we're calling the width here, but we could also look at it as the height. The height of this particular rectangle is just going to be the y value here. So what I need to be able to do is somehow characterize that, okay? Now, in this case, since I just have a rectangle and a triangle to work with, I could use what I know about similar triangles to work. We know that similar triangles have proportional sides and the angles are equal. So what I'm showing you up here are the two triangles that are similar to one another that I'm going to use, okay? So, well, actually, this is just one, but I'm going to show you the other one down here. So what I've done here is I've taken the triangle EBA, and noting that since it is an isosceles triangle, where my hypotenuse is 14 units, and knowing that any isosceles right triangle follows this format, what I know is that both of these sides here will have to be essentially what the hypotenuse is divided by square root of 2, okay? And so that's what I'm stating here, that a times square root of 2 would have to be 14. So if I divide both sides by square root of 2, I get 7 times square root of 2, and that's what a would be. And so here, that's why I have that length there. Now that I know that, the two triangles that I need to look at that are similar to one another are going to be this right triangle here, which is, if we look at it, it is going to be the triangle. I'm going to do this in a different color here. It's going to be the triangle ACB. So that big triangle. And then we're going to look at this smaller triangle here. Probably can't see that, so let's use a different color here. I'll use this one, yeah. So we have this A, D, and P, okay? So we got big right triangle here, and we have smaller right triangle here. And so that's what I'm showing you here and here. We know that for the bigger right triangle, we know that the side from B to A down here, that length is 7 times square root of 2 because of what we found over here. And thus we also know, since this is the hypotenuse of this triangle over here, which means that 7 times square root of 2 is the hypotenuse of our triangle here, then we just have to divide this by square root of 2 to figure out what these sides are, and it'll just be 7. Okay. So now that we have this, then of course, similar triangles, sides are proportional, angles are the same. So we could essentially say here that if we're looking at this correctly, this side is to this side as, well, so yeah, this side is to this side as this side is to this side, okay? And so the main thing here, and this is why I say if we just use geometry and a little common sense, we don't have to do a whole equation of a line thing. If I have a similar triangle here, and this is 7 and that's 7, then that's telling me that whatever this length is should be the same thing as that is. Okay, so I can simply just look here and say, hey, this is similar right triangles. So since the base of the smaller right isosceles right triangle is 7 minus x, then that means that the height of it also has to be 7 minus x. And so that's how we get what y is going to be in terms of x. Now from here, everything else is relatively easy. We know that for the area, we're going to model area as just x times y, where we know y is just going to be 7 minus x. Okay, so pretty simple. So we see that we have all that info there. Oh, okay, I see here I did it actually the opposite. So let me switch that around here. Matter of fact, I'll just erase it. But it doesn't matter what we call x, what we call y, we end up getting the same thing. The main thing to remember here is that notice that the length of our rectangle again, since x has to be considered length, I divided it in half so that I could look at this, look at this whole width here as 2x. So the length of the whole base of this rectangle here is just going to be 2 times whatever that amount is. The length of it, which really is like the height in this case, is just 7 minus x. So we have the situation here. We multiply, and again we have our quadratic function or parabola that opens down. So we're expecting this to be a local max, and we're going to use either the first or second derivative test to show that. So in this case, we take the derivative of our area here, which is just going to be 14 minus 4x, set it equal to 0, and we see that once we solve for x, we get 17 over 2. Now, again, since we had a quadratic function for the area to begin with, we know that if we take the second derivative of area, we're just going to get some constant. And so we see that because if I take the derivative of 14 minus 4x, this is going to give me a minus 4. And this negative 4 here lets me know that, for the second derivative, lets me know that my function is going to be concave down for all values of x. So that means it'll definitely be concave down for values of x in between 0 to 7. And that's important here. Let me erase some of this, because in all of what you're seeing here, x can go from 0 to 7. Okay, so that's why I made that statement there. Thus, we know that at this critical value of 7 over 2, which is 3.5 units, we know that we're going to have a local max. And so because of that, we know that the max area here will be 49 over 2 units. Okay. And we know that the dimensions, once we start plugging everything in, is going to be 3.5 units by 7 units. Okay. And of course, for the max area, once we knew what x was, of course we knew that y was just 7 minus x. We just plug that in. Area is just going to be x times y, and you see here how it just all works. And so if you're asked to find the maximum area, just once you figure out what the critical value is, plug that in for x here, figure out what y is, multiply it times x, you're done. If you need to know the dimensions, then you need to leave them separate, meaning don't multiply them together. Okay. All right, let's move on to the next example. Okay, so for the next example that we have, we want to find the volume of the largest right circular cone that can be inscribed in the sphere of radius 7. Okay, and so hopefully you can see this, but we have our sphere here. And basically what we're doing is saying that, hey, we have some sphere and we want to stick a right circular cone into it. We want to figure out the largest one we can stick in there. So to put this in layman's terms, we have a big paper cone that we're trying to stick inside of a ball. And we're trying to see the largest cone we can stick inside of the ball. Okay. Now, we know that the volume for a right circular cone is calculated by 1/3 pi r squared h. And so we're using that as a guide to help us to be able to figure out what's going to be, of course, the volume of the largest right circular cone. That's what we want to know. Now, things that we need to define are, first, what is going to be the radius of the right circular cone, okay? And that's what this length x is here. We also have the height of the circular cone, which is going to be the length from here to here, which is 7 plus y. Okay? And here what we are going to do is we're choosing to rewrite or model everything in terms of y here, because that's tied to the height of the circular cone, and it will be a little bit easier for us to model it that way versus try to model everything in terms of x. So we're basically wanting to figure out, now that we know the height in terms of y, I want to know what is going to be x in terms of y. Okay. Now, what you see here, and this is going to be the key to doing this problem, this point right here is the center of the sphere. Okay. And so for this 3D figure, no matter what direction we go, if we go from that point to the edge of the sphere, the lengths are always going to be the same. Okay. And so we see that from this particular point, if we go in this direction and we hit the surface of the sphere, that length is going to be 7. And of course, you see here, we've made a right triangle with the radius of the sphere, this portion of the height of the right circular cone, and the radius of the right circular cone. And so what you see here is for that little small right triangle, we just need to find out what x is in terms of y. So it's just the theorem that's better known as Pythagoras Theorem, but it's really not Pythagoras Theorem. We see here that we just basically need to solve for x. And in doing this, we remember here that x is actually going to be r, which is going to be the radius of the right circular cone here. Okay, so let's go back up here just to make sure that we get that. Remember, the radius of the sphere is 7. That's totally different. That's constant. That's not changing. Okay. The radius of the right circular cone will change based upon how big the cone is. Okay. And so that's why I'm renaming the what we normally use R, which is the radius. And that's actually coming from here, radius of the right circular cone. That's the same thing as X in this particular right triangle here. Okay. So with that, I just use the relationship in between 3 sides of a right triangle to figure out what is going to be the radius squared, or X squared, in terms of Y. And we see that it's just 49 minus Y squared in this case. So once we have that, what we see here is that we pretty much have everything that we need to know. And why is that? We needed to be able to somehow express both R squared and H in terms of the same variable. And we see here that we did R squared in terms of Y, and we did H in terms of Y. So now that we have those two things, we could substitute R squared and H for these expressions respectively, and that's exactly what we see we have right here. From that point, it's just a matter of trying to figure out what is going to be our volume, taking the derivative of volume with respect to Y, setting it equal to 0, and then figuring out what our critical value would be. Now, in this current form, we see that we have the volume of our right circular cone in terms of Y and factored out, but it's going to be, you can go ahead and multiply out everything and then have everything in terms of, like Y cubed, something Y cubed plus something Y squared. But to me, I found it easier just to leave it in factored form here and just utilize the product rule and the chain rule. Okay, that way I didn't have to deal with any huge numbers that may have resulted here. So we just take the derivative of our function, set it equal to 0, and again, for what we see up here, I'm just using the product rule to multiply, to take the derivative of this. Okay, so derivative of the first times the second plus first times derivative of the second. Okay, so that's all that is here. Clean stuff up, and then eventually I get it to looking to where we have the situation here, and now I'm just trying to solve for Y. Okay, so I'm just working, trying to solve for Y. And of course, at this point, I'm going ahead and I'm actually multiplying everything through here. Note that I could have actually come up here and say, since I have a 7 plus Y here and I have 2 of them there, I could have just said this. But here, if I would have done that, I would have had to ensure that Y equals -7 couldn't be a value. And I didn't want to go through all that, even though it's easy to do. I just didn't want to do that, so I just multiplied everything out. And so once I get to that point here, then I see that I have this quadratic equation. I factor it out, and I see here that my value ends up being 7/3 and -7. And again, just like how I was telling you here, I wouldn't be able to have -7 as an answer, just because when we're talking about length or height in this case, it always has to be non-negative. And so with that, we see that our critical value is 7/3. And at this point, all I need to do is take 7/3, plug it back into the derivative of my function. And what I would probably do is use this form of the derivative to make life easy on myself. plug that back in to see, am I going to get a positive or negative value? Okay. And so in this case, I decided to actually do both the first and the second derivative test, since I've been sort of favoring the second derivative test for most of these. So I'll go over the first derivative test here. So we see that for the first derivative test, we would need the first derivative. And so this is the formula for the first derivative. And this is what it is, more simplified. I pick values to the left and to the right of my critical value, and I just plug it in to see what do I get. And what you see here is that when I plug in 1, which is to the left of 7/3, I'm going to get a positive value for the derivative. And when I plug in 3 into it, I'm going to get a negative value. So you see that down here. And so because I went from having positive first derivative values to negative first derivative values, I know that my graph here had a local max there, which is in turn a global max at x equals 7/3. And thus, if I just plug in 7/3, plug it into the formula for volume for this right circular cone, we see that we get this result here of 10,976 divided by 81 times pi cubic units. Okay. Now, of course, if we would have done this the second derivative test way, I would have had to take the derivative of the derivative again, got this result, plug in the critical value, and you would have seen I got a negative result for the second derivative, which lets me know my graph is concave down. Thus, my critical value would have to be at a local max, and since it's the only one, it will be a global max. All right, so let's move on to what I think is going to be our last example. All right, so for this example, this is an example to where we have a woman and she's living on this island, and it's kind of close to like the mainland, but you know, she has like her own island, so I'm assuming that she's rich. And I think they have some places like this up in New York. So or just areas where they have, you know, a lot of small little islands connected to, you know, bigger land masses, so, or close to bigger land masses, I should say. But she's basically living on this island, and she's going to go to this little small town down here to basically go get supplies. And so she's trying to figure out which way to go. Should she just come straight across here and row a boat 6 miles to do that? Should she just say, all right, well, I'm just going to start at this point here and just row all the way here? Okay. And so if she comes from here and rows all the way here, she's going to be doing all rowing the boat and no walking. Whereas if she comes and does it this way, she's going to row her boat a little bit, but then she has to walk a lot. And so what she wants to do is find the happy compromise, a happy medium in between, to where she does just enough rowing of the boat and just enough walking to be able to get there as fast as possible. Okay. So that is essentially what this problem is about. And what we want to do is figure out at what landing point this lady has to be at in order for her to get to town the fastest. So we're trying to figure out this point that I'm drawing here. Where should that actually be? And this point is going to be in reference to where she would be if she would just come straight across from her home island here. If she just went straight across and then started at point P here. Okay. Now we get some specific information about how fast she could row a boat, how fast she can walk. Okay. And that's going to help us to be able to sort of come up with an equation to characterize what it is that we need to know here. Okay. So we have a small island, 6 miles from the nearest point, straight shoreline. We know that the woman can row at a rate of 3 miles per hour. and she can walk at a rate of 4 miles per hour. And I'm saying the word rate like that because that's going to help us to be able to figure out what it is that we need to do. Okay. And I'm saying that because we know rate is just going to be the quotient of distance and time. In other words, we know that distance is equal to rate times time, and somehow, some way, we're going to use that equation to help us to be able to model what it is that we need to know. Okay. Now, we know our rate to row a boat is 3 miles per hour. Rate to walk is 4 miles per hour. And we know that from point P to where town is going to be 15 miles. Okay. And so we want her to get there in the least amount of time. So the thing is we want to minimize time. And in terms of distance equals rate times time, time is distance divided by rate. So if we have a way to characterize distance and characterize rate all in terms of one variable, then we can come up with an equation for time and minimize it by taking the derivative of it, setting it equal to 0, and figuring out the critical value and confirming that that critical value is going to be at a local minimum. So that's our plan here. Okay. So the note that I have here is that we need to find x such that t, which is time, is going to be minimized. And so notice here in our model, we know that we want to figure out where this landing point is. I'm just going to put it in a different. We want to figure out where she needs to land at. And so that's going to be x units away from where point P is. So that's how we're going to model everything. So we need to have everything written in terms of x. So we assess a few things. So the first thing that we assess here is that what I'm calling R here, that's going to be the distance from the island to the landing point. Okay. So that's going to be R right there. X is going to be the distance from point P to the landing point. So that's from basically here to here. And of course, 15 minus X is the remainder of what this is from this point, from the landing point on to town. Okay. Now again, distance equals rate times time lets us know that time is equal to distance divided by rate. And so the two rates that we have to help us to be able to characterize this is we know how fast she rows, we know how fast she walks. Okay. And so if we look here, I'm going to erase some of this. Let's get rid of this. All right. All right, so the first thing that we want to do here is try to model what it's going to look like time-wise if she's coming from the island right here and she's rowing into this landing point right here. Okay. Now, this distance here again is going to be R. Okay. And so that's why we have this here. Notice that we have a right triangle made with R, the 6 miles across here, and X here. So that's why I have this here. And thus R is just going to be the hypotenuse of this right triangle, which is just 6 squared plus, x squared plus 6 squared, and take the square root of that. So that's how we get the square root of x squared plus 36. Okay. So this will characterize the distance that we need if she's rowing. Okay. So notice here that if she's rowing, distance is going to be this, And of course, the rate is going to be this 3 miles per hour. So we could literally take square root of x squared plus 36, divide that by 3, and that's going to be the time that it takes rowing in terms of this variable x here. Okay. Now, if we do the same thing by walking, I'm going to erase this again. Of course, the total distance that she has to walk is, if she's walking, is going to be this 15 miles. Okay. And we know that her rate of walking is going to be, 4 miles per hour, right? But the thing is that that's the total distance, 15 miles. We don't want her to walk the whole 15 miles. We just want her to walk from the landing point. So from the landing point to town, that distance is 15 minus x, okay? And so we'll take the 15 minus x as our distance and divide that by our rate of walking, which is 4 miles per hour, okay? And so now you see that if we take all that into consideration, this is the time you row. This is the time for walking in terms of distance divided by rate. And notice here that I have this time equation in terms of how far she is from point P. And this problem only makes sense from 0 to 15, meaning that the most that she could walk would be 15 miles, okay? Now, the fact that our domain for this problem is in a closed interval here, what this does is that this sets us up for using what's called the closed interval method. And if you remember from the earlier videos, of course, if you've been watching them in succession here, these earlier videos, the closed interval method is our way of systematically trying to figure out if we have a global max and or global min by using critical values, okay? And so we can only do this whenever we have a situation where we have a continuous function over a closed interval, okay? AKA the extreme value theorem. Whenever we have a continuous function over a closed interval, we're guaranteed to have at least one global max and at least one global min, okay? And so that's essentially what we're going to be using here. So I'm going to skip all this. So now that we have this time equation, we just take the derivative of it, find our critical value or values, and then since we have this under a closed interval, the closed interval method says that we need to not only figure out what is going to be not t prime. So not only what is t of our critical values, and I'm assuming that we may have more than one, we also need to figure out what is t of 0 and t of 15 and compare those to see which number is going to be the smallest, okay? So I come here, take the derivative of this function t of x here. And of course, you can see me going through all that. I won't bore you with the details on it, but the end result ends up being this 1/3 x times x squared plus 36 raised to the minus 1/2 minus 4. And then I set that equal to 0. And I've changed the way that this looks from fractional exponent form into root form because it's going to be easier for me to solve it that way. And so after I go through all the business of trying to solve for x here, you can see that on this next page, I finally arrive at a critical value of 18 divided by square root of 7, okay? Now, I actually have plus or minus here because of the fact that going from this step to this step, I have to take the principal root of both sides here. But again, it doesn't make sense for me to look at negative distance because there's no such thing as negative distance. So I have to look at only non-negative answers here. And so that's why we just have 18 divided by square root of 7. Okay. And again, for those of you that need to know what that is in decimal form, that's going to be about 6.8. Okay. So now, according to the closed interval method, what we need to do is figure out what is t of 0, t of 18 divided by square root of 7, and t of 15 to figure out which result will give us the smallest time. Okay. And so we see here by plugging in 0, 18 divided by square root of 7, and 15 into all those, we see that the 18 divided by square root of 7 time, or what is it, the 6.8, and I forget what units we actually had here. I think that's in hours, I believe. Yeah, because we did everything in miles per hour. Yeah, so that's what that was. So, sorry, not that's what the time is, but the x is the actual distance, and the distance here is in miles. Yeah, because so x is in miles here. So when we see this 18 divided by square root of 7 here, that's actually in miles. So that would be like 6.8 miles. So when our landing point is 6.8 miles from point P, it's going to take the woman about a little over 5 hours to be able to get into town. And as you can see from all the other numbers, that is going to be the quickest time possible. Okay. So the boat should be landed at approximately 6.8 miles from point P in order for the woman to have the shortest time to travel to town. Okay. Now, the last thing that I mentioned here is that we could have actually did the second derivative test for this, but I specifically wanted to do this problem to show you that whenever we have those closed intervals that we could do, the closed interval method for it. But here, if we would have done the second derivative test, of course, it would be more involved because the fact that we would have to take the second derivative of this function t that's already was kind of hard to take the first derivative of it. But you see how I've kind of gone through all that, taking the derivative, and then afterwards, we would plug in our critical value into the second derivative, and we see that that result ended up being a positive value. And since that result was positive, what we see is that our original function, or t of x in this case, whatever it looked like, it would be concave up at the 6.8 mile mark, or the 18 divided by square root of 7 mile mark. And thus that would tell us that we have a local min at the 6.8 mile mark, which also means that we have a global min because it's the only one. Okay, and so that's another way we could have actually approached this problem. But again, notice that if you compare trying to take the second derivative of this and doing all this business here versus just using the closed interval method, I'm pretty sure you would want to use the closed interval method. Okay, much easier to do, and you get the same result. All right, so with this being said, this concludes the video that I have on optimization problems. And remember that the best way you get good at word problems is just to expose yourself to as many of them as possible and practice as many of them as possible. So I hope that these examples here sort of help you to be able to understand how to attack these sort of problems. Take care.